Here's introducing Mekkaew. Mekkaew is quite famous as an amateur road cyclist in Singapore. However, the fact is he's also a design analyst and has a vast amount of experiences in analyzing products used in different applications. Today, he's going to share a few things on the design of a bicycle. Typically, the bicycle is subject to multiple kinds of loads, and the basic one would be the static loads. The result of this simulation would be to understand the stresses, reflection, and of course improve the design based on these outputs. And there are on a cyclic load leading to fatigue failure is one of the most relevant loading conditions. The best component to understand this scenario is the crank. Check out, crank is subject to a load through the power created by the legs. It rotates consistently as well. Cyclist strives to maintain a consistent RPM of 80 to 100, creating a fatigue load. Now, let's see how we simulate this in SolidWorks Simulation. One of the things which I emphasize for any analyst is to have a goal before starting off with the software. Aimless simulation can only lead to colorful plots, and that's not what we are interested in. Now, in this case, we typically look at having almost an infinite life and of course the lightest crank. Let's start with seeing a few failed cranks. You can see how bad it can get. Worse, the accident that it can cause is more damaging. It leads to injuries to cyclists. One can see that most of these cranks are fail because of fatigue. Most of these fail are due to fatigue, and durability can be one of the biggest problems. Hence, we need to understand the exact life of this part. This can also help in deciding warranty. And as a designer, Mekkaew is confused on which would be the best design that can serve the purpose of being light and strong. We can see three variations of the crank, and it is indeed a tough decision on which is the best option. SolidWorks Simulation can help in taking this particular decision. To start with, let's take a particular design which is created using experience and see how simulation can help to meet our goals. The pedal is subject to a loading of 1,350 Newton. This is the force that the rider puts on the pedal. Our goal is to have the pedal to sustain 7 million cycles, which is considered infinite life. Now, let's move on to SolidWorks Simulation. Here is the crank with 2 gears. Typically, road bikes have 2 gears in the front. However, in this simulation, let us concentrate on the crank. Hence, we can suppress the gears and use the crank and pedal only for this simulation. SolidWorks has this fabulous feature called configuration. Using configuration, we can create one for design and create one more for simulation. Consecutively, we can create configuration for different variation of the design. Let's start with the first design. Here it is. We start creating a new study. Either a wizard can be used to set up the basics, or we can create it directly. Next, we define the material properties. We can either take the material from the database or create our own material database. So in this case, we are using material from the database and modify it by adding the SN curve necessary for fatigue simulation. The assembly consists of two important components, the crank and the pedal. We assume that these two are bonded to each other. This crank is rotating around the shaft. We are using a hinged restraint here. And the crank is connected to the gears, which transfer the load to the chain and finally to the ties. There is a hinge restraint also defined at this location. The terminology is similar to what designer can understand, and he doesn't need to worry about it. Finally, we apply the load on the pedal, which is 1,350 Newton. That's it. We solve and ready to see the result. Let's see deflection. 4+ millimeters. Huge, but a reference for us. Stress 215 MPa, quite close to the U of 270 MPa. And it has a factor of safety of 1.28. Now, let's move to fatigue. The minimum life is 4 million cycles. The most important input given here is the SN curve. Either it can be derived from elastic modulus, ASME, or we can input it manually to SolidWorks Simulation. Now, let's see the second alternative. One can see the benefit of integration here. I just need to create a new design in a new configuration and copy the entire simulation setup to this new configuration. I'm not dwelling in detail the design changes. However, one can see that the design has been improved at the location where the stresses were more. Let's see how we replicate. I just use copy, select the right configuration. All set, new setup is ready to solve. Solve and get the results. Let's do a quick review. Displacement 3.5 millimeters. Maximum stress location has changed and reduced to 198 MPa. A factor of safety has also improved to 1.3. And more importantly, during fatigue life, we see that it's well above our target of 7 million cycles. Finally, let's move on to the third design. Here are the results. Let's see the absolute value through the slide. Design 1, we saw this value, life of 4 million. Design 2, good improvement, life of 14 million. Design 3, 13 million, but it has its own hurdle in the form of factor of safety and stresses. So, for these design iterations, if we concentrate on life, then definitively design 2 is the best. So, in this way, we see how SolidWorks Simulation can help to improve the design and take the right decision on which is the best design for a given scenario. And the designer can decide this with confidence and valid data to prove his decision.